So today we are going to start this journey of deriving conservation of mass, momentum and energy in the differential form. So to start with, we will get started with conservation of mass, which is generally called as continuity equation. I would be addressing this as continuity equation downstream. So to do this, we need to invoke what is called as Reynolds transport theorem, which you would have either studied in thermodynamics or in fluid mechanics. Without deriving that, I am going to invoke that equation and use that. So you have this Reynolds transport theorem. So let's go and start writing this derivation. Okay, so that is continuity equation. Okay, so here we have Reynolds, by Reynolds transport theorem, Reynolds transport theorem, you have dB system divided by dt is equal to dou by dou t of rho small b dV, which is volume, rho is density, b is some unit, what is that I will let you know in a while. CV means control volume, and rho b v dot n dA across control surface. CV means control volume, CS means control surface. Now B can be any parameter, but for conservation of mass, B is equal to simply 1. But capital B is m into small b. M is mass. Okay. Now what does that physically mean? You don't understand with these terms. So let us write, that is time rate of change of the mass of the coincident system. On the left hand side, you have what is called as the equation which you can apply for the system, and that is for conservation of mass. Mass is conserved of the system, we know that. But now how do I apply for control volume? If I have to do that, if I have to apply for control volume, I have to apply RTT, that is Reynolds transport theorem. That is, RTT is a tool to transform the conservation of mass, momentum, energy from system to control volume. How can I apply the rules or the conservation rule principles which I have applied for mass, momentum and energy for a system to control volume? So that is what is done through Reynolds transport theorem. So left hand side is for the system, the right hand side is time rate of change, mass, time rate of change of mass of the contents of the coincident control volume. That is where at a given instant where system and control volume are coincident. This is this term. Now plus net rate of flow of mass through the control surface. So if you through the control surface, so you will understand what it means in a little while. So this is this term. So basically RTT is a theorem which transforms, which can help us to apply the conservation principles which are applied for a system, how we can transform them or apply them to the control volume. That is the main idea. So here for conservation of mass, B equal to 1, and we know that dm system by dt, that is the mass of the system is conserved. That means mass of the system does not vary with time or space, that means it is 0. So, that means the above equation reduces to dou by dou t rho b dv, b is 1, so rho dv of the control volume plus rho v dot n dA. N is a normal vector, normal to the controlled surface, v is the velocity vector, v is the velocity vector, now is equal to 0. So, now let us take this equation and get this each term. So, to get this term, each term, so what do I do is I will take a parallelepiped, that is I just take a rectangular block whose dimensions are delta x, delta y, delta z. Okay. So, now this is the parallelepiped. Now, there are two terms here, that is dou by dou t of rho Cv of the control volume, rho dv plus Cs rho v dot n dA equal to 0, that is what we said. So, the first term dou by dou t of rho dv is nothing but the dv is delta x for the control volume, that is nothing but delta x, delta y, delta z. So, dou rho by dou t into delta x, delta y, delta z, that is the first term. Now, let us try to write what will comprise for this second term, that is actually the mass flow rate, rho v dot n dA, that is rho into A into velocity, that is mass flow rate. So, how do I get that? That is, if I take the plane delta y, delta z, rho into the velocity in the x direction is u over the area delta y, delta z. Okay. And what is entering here? That is rho v delta x, delta z in the x direction, and in the z direction you have rho w delta x, delta y. Okay. So, now what is coming out by Taylor series expansion, that is if you have f of x plus delta x, you get f of x plus del of f of x by del x dx plus del squared f of x by del x squared into delta x whole squared 1 by 2 factorial, so on and so forth. But if I take only this and my f of x plus dx is u, that is rho u del y by del z is f of x plus dou of rho u by dou x into delta x, delta y, delta z is constant, so that is why I have pulled out. So, this is written on the basis of Taylor series expansion. That is for the x axis, flow rate in the x axis. Now, what about in the y axis? So, if you write in the y axis, you have rho v dx dz plus dou of rho v by dou y dy into dx dz. Similarly, what is getting out here is that w, that is rho w delta x delta y, rho w delta x delta y plus dou of rho w by dou z into dz into delta z into delta x delta y, delta z delta x delta y. Okay. So, now we are writing, remember we are doing this across the control surface. My control surface is the surfaces of my parallelepiped. So, now in whatever is getting in, mass in always will be negative, because the cos theta is going to be between the vector, that is it is going to be negative. The mass flow rate in always is negative and mass flow rate out will be positive because of V dot n. V dot n, that is V normal vector, which is V into cos theta. So that becomes negative and V cos 180 becomes positive. V cos 180 is negative and V cos 0 is positive. Okay. So that is what is happening, why mass flow rate in is negative. So you have what is called rho u del y delta y delta z. Remember, I am writing Cs rho v dot n dA, that is rho u delta y delta z plus this is minus plus rho u, this is next term is this rho u delta y delta z plus dou of rho u by dou x delta y delta z plus this term rho v delta x delta z, not plus, mass flow rate in is minus, plus rho v delta x delta z. Now I am writing this term plus dou of rho v by dou y delta x delta y delta z. Now similarly minus of rho w, that is this term rho w delta x delta y plus rho w delta x delta y plus dou of rho w by dou z delta x delta y delta z. Okay. If you really see here, this gets cancelled out, this gets cancelled out, this gets cancelled out. So I am left with this term and this term. So that will be dou of rho u by dou x plus dou of rho v by dou y plus dou of rho w by dou z into delta x delta y delta z. Remember, there is one more term. We are trying to write this equation. So one of the terms is dou rho by dou t delta x delta y delta z, other term is this. So if you take delta x delta y delta z as common, so you get dou rho by dou t, this is coming from this term, this is coming from this term dou rho by dou t, but I am not writing delta x delta y delta z because I have taken common, plus dou rho u plus dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is equal to 0. This is one of the forms of the continuity equation. We have almost arrived, but there are different forms which we will be invoking subsequently. That is why we should be conversant with all of them. So if we take up the next one, that is if we just expand this, so what do I get? Dou rho by dou t. So I keep rho constant and write u, differentiate u and subsequently the other one, that is u dou rho by dou x plus rho dou u by dou x, that is by differentiating I am getting, plus again v constant dou rho by dou y plus rho constant, now differentiate with y, dou v by dou y plus w dou rho by dou z plus rho constant dou w by dou z, all of this is equal to 0. Right. Now this term can be written as the total derivative d rho by dt is the term. So, what does that mean is that it is the density varying with time and density varying with space. Density is varying with x, density is varying with y, density is varying with z by virtue of convection parameter velocity u. So, this is transient term, this is the variation because of convection, because the fluid particle is moving with a velocity u, that will cause the density variation with the space at different locations. So, this is called as total derivative of density. Okay, that is d rho by dt plus rho of dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So, this is another form of the continuity equation. Remember, this is applicable for both compressible and incompressible flows. I have not made any differentiation, it is applicable, it is a generic equation, it is a generic equation. But if it is for compressible flow, if it is for compressible flow, you have, this is the equation. Now, for incompressible flow, what will happen is that we can even write this d rho by dou t dt plus rho of vectorially del dot v equal to 0. But for incompressible flows, you have d rho, density is constant, neither it varies with space nor with time. So, that is constant and uniform. So, then in that case d rho by dt equal to 0. So, that is we get del u by del x plus del v by del y plus del w by del z is equal to 0. If you recall, in my previous class we derived for incompressible flows, we called this as a dilation rate, and for incompressible flows we said that dilation rate is 0. So, you see, from different form also we got the same equation. So, the takeaway is that I would like to emphasize that you should remember the three forms of the continuity equation, that is, one is this dou rho by dou t plus dou by dou x of rho u by plus dou rho v by dou y plus dou rho w by dou z equal to 0. That is one form. Another form is this d rho by dt plus rho del dot v is equal to 0, and of course, this gets reduced to incompressible flows, this gets reduced to del dot v equal to 0. Okay? That is about the continuity equation. So, now let us move on to conservation of momentum. So, you know that for a system, rate of change of momentum of a system equal to sum of the forces acting on the system. You know that rate of change of momentum of the system is equal to sum of the forces acting on the system. But in fluid dynamics, you have to apply to control volume. So, how do I apply to control volume? Again, I have to use Reynolds transport theorem to transform the equations which are written for system or the principles applied for the system to control volume. So, like what we did earlier. So what do we do is the conservation, the RTT is that dB system by dt is equal to dou by dou T of control volume rho B dV plus control surface rho B V dot N dA. Now, here for conservation of momentum, B will be equal to mass, that is mass into velocity, mass flow rate into velocity will become the momentum. So, that is why it is B equal to m. If you put that, so what do is that I get is dou by dou T of rho V d, sorry, not m, this is V. So, volume, because that makes it volume, rho V velocity, this is velocity, this is velocity. So, rho V dV, then only you will get the momentum. So, plus V rho V dot N dA, you can see that this is mass flow rate and this is velocity. So, you get momentum. Okay. So, this is across the control surface, which is equal to the sum of the forces. You can see here, this is the rate of the change of the momentum of the system, that is what we did applied through RTT for the control volume, and now the sum of the forces acting on the system, same forces which are acting on the control volume, sigma of F acting on the contents of control volume. So, this is, how do I write this? That is rate of increase of x momentum. There are three equations, one is x momentum, y momentum, z momentum. I will derive for x momentum, y and z, we can directly infer from this derivation and write. This is rate of increase of x momentum, that is dou by dou T of control volume rho V dV. V is velocity and this is volume, plus minus of rate at which x momentum enters plus rate at which x momentum leaves. How did I write these two? That is plus V rho V dot N dA, that is these two terms are coming from here, is equal to sum of the x component forces acting on the fluid in the control volume, that is equal to sigma of FCV. So, now let us take up one by one and try to derive this the momentum, x momentum, what it is entering. Okay. So, what is that? So, what we would do is rate at which the x momentum enters and leaves. So, let us draw this. So, if you take a parallelepiped, what you did for conservation of mass, similar to that if you do, so you have a parallelepiped. Okay. So, this is your delta x, delta y, delta z. Now, the rate of change of momentum entering, x momentum entering, mass flow rate into velocity. The mass flow rate is rho u, area is delta y, delta x, delta z, that is the mass flow rate which is flowing across this plane delta y, delta z. And what is the x momentum it carries? That is multiplied with velocity. Mass flow rate into velocity gives you the rate of change of momentum. Now, what is getting out? Again, by Taylor series expansion, you have u into rho u delta y delta z plus del of rho into u rho u squared by del x into delta x delta y delta z. That is by Taylor series expansion series, the way we wrote earlier I have written. Similarly, this is very important term, please listen to me carefully. You have the mass flow rate with which it is flowing in the y direction is rho v delta x delta z. This is the flow rate which is flowing in the y direction. But then what is that x momentum it carries along with it? So that is the x velocity u. So this is where people get confused. So this is the mass flow rate in the y direction, but it carries, here I am trying to bookkeep the conservation of the momentum in the x direction. So that means the x momentum is carried because of the virtue of, or by virtue of velocity u for the flow rate of rho v delta x delta z. So here you get u into rho v delta x delta z plus dou of rho u v divided by dou y into delta y delta x delta z. Now I would give this as a exercise, you can write it yourself, that is rho w delta x delta y. This is the mass flow rate flowing in the z direction. But what is its x momentum, what it is carrying? That is because of the virtue of velocity u. So now u into rho w delta x delta y plus dou of rho u w divided by dou z into delta z into delta x delta y. Okay. So this is what you get. So now as you can see that what all is entering these terms are tending to be negative, they will be negative, as you can see in the previous equation. Entering term is negative and getting out term is positive. So these terms are positive. Then if you do that, this term gets cancelled out, this term gets cancelled out, this term gets cancelled out. So you have dou of rho u squared by dou x plus dou of rho u v by dou y plus dou rho u w by dou z into delta x delta y delta z. So that is about the conservation of momentum bookkeeping. So in the next class we will continue this and try to combine the left hand side, right hand side and get the Cauchy's equation and finally the Navier-Stokes equation. So we are in the middle of the derivation of Navier-Stokes equation or conservation of momentum of the x momentum. Thank you.